What type of gel will suit your experiment well? How do you choose which type of gel to use? Let's talk about things like agarose versus polyacrylamide, denaturing, non-denaturing, what percentage of gel, what buffer, all those various options that you have when you're doing gel electrophoresis.
With any type of gel electrophoresis, the basic idea is the same. We're taking molecules, these can be proteins, these can be RNA or DNA, and we're going to separate them by size. And we do this by sending them traveling through this gel mesh. The bigger the molecules are, the more tangled up they're going to get, the slower they're going to move. The smaller the molecules are, the easier they're going to be able to kind of wiggle their way through the gel. In both of these cases, we're going to get them to move through the gel by setting up an electric charge gradient where we have a positive charge on one end and a negative charge on the other end. We're going to load our samples on the negative charged end, and we're going to make it so our samples are negatively charged, either because they naturally are in the case of DNA or RNA, or we can make them negatively charged with proteins with using SDS. These negatively charged molecules are then going to be motivated to move through the gel, but then they're going to be slowed down based on their size and based on how meshy the gel is. When we turn off the power, we stop them in place. The bigger molecules are then going to be higher up than the smaller molecules because the bigger molecules, they would have been traveling slower, and so they wouldn't have gotten as far. And then we can look and we can see, okay, well, with how many things are in here and what are the relative sizes and how do they compare to like a ladder of known sizes, like a molecular weight standard. And so that's the basic idea of gel electrophoresis, but then there are a lot of different flavors. And so one of the key decisions you have to make is going to be like what type of gel you want to use, both in terms of what the gel is made up of. So is it made up of agarose? Is it made up of the sugar? Or is it made up of polyacrylamide? So a page gel, polyacrylamide gel electrophoresis, or page. And then when we have these, so agarose is going to be better for separating big things. So we often use this for separating big DNA pieces, such as maybe if you did a PCR reaction or you're doing some cloning, you're often using an agarose gel. And in the case of smaller things, so when we're talking about smaller DNA or RNA, or when we're talking about protein, in that case, we're typically going to be using a polyacrylamide gel. So we're using one of these page gels. And so the page gels are going to be kind of like these vertical thin slabs between pieces of plastic or between pieces of glass. And then your agarose are going to be these horizontal slabs. And in both of these cases, we can kind of customize how meshy they are and how good they are at separating bigger versus smaller things. And so, as I mentioned, we often use the agarose for separating bigger things and the polyacrylamide for separating smaller things. And this is because that polyacrylamide is going to have a finer mesh. It's going to be a tighter mesh and a more consistent mesh. And in the tighter that mesh is, the better it's going to be for separating smaller things. If you imagine big things versus small things trying to travel through one of these meshier meshes, then it's going to basically, the small things are going to get slowed down with this high percentage, whereas they'd be able to just kind of flow straight through this low percentage. And so if you want to separate small things, you're going to want to use a higher percentage. But if you have bigger things that you want to separate, now the low percentage is going to do a good job, whereas the high percentage, they're all kind of going to be like way bigger than those pores, so they might not travel very far if they can even get into the gel itself. And so we can customize how meshy the gel is by increasing or decreasing the percentage. And so this would be the percentage of the agarose in your gel, or in the case of a polyacrylamide gel, the percentage of those acrylamide pieces that you're piecing together using, basically, you're doing the polymerization. And so you can either, if you're making them yourself, you can use whatever percentage you want to make, or when you're buying them pre-made, they typically have a set of different percentages that you can choose from. And another option is a gradient gel if you have a kind of range in sizes that you want to separate. So it's going to have a tighter mesh at the bottom so you can separate smaller things, and a looser mesh at the top so you can separate bigger things. And so you're able to separate a wide range of sizes, but you don't get as good of resolution or separation of things that are of your design of one size versus another. So for example, with a high percentage of gel, you're able to get good separation of these smaller things, but not as good of these bigger things. With the lower percentage gel, so those bigger pores, you're able to get better separation of these bigger things, but not of the smaller things. And then with the gradient gel, you're kind of able to get okay separation of everything. And so commonly you might see like a 4 to 15%, a 4 to 20%. With all of these, you can look online and look at charts and things like this to see what percentage is best for the size of the molecules that you are interested in separating. So that was one decision. Okay, do we want agarose gel? Do we want polyacrylamide gel? So polyacrylamide we can use for proteins or for nucleic acids. We typically use agarose gels for nucleic acids, but only the big ones. And so polyacrylamide gels are going to be used for those smaller pieces. So if we're talking about things in the hundreds of nucleotides, we're often using polyacrylamide gels. And when we're talking about going up in the kilobases and things like this, we're talking about using agarose gel electrophoresis. Another option we have to make is, do we want denaturing conditions or non-denaturing conditions? Or non-denaturing is often referred to as like native. So when we talk about denaturing, what we're referring to here is basically unfolding the molecules and separating them from one another. And so in the case of a protein, we're going to be unfolding the proteins and breaking up the protein-protein interactions. For nucleic acids, here we're going to be separating strands of DNA. We're going to be unfolding any hairpins or other structures in the RNA. And when we do this, well, now we're going to have a linear relationship between the how big these molecules look like they are, and then how far they travel. And so basically, when we have them traveling through the gel, they're going to be traveling based on how kind of big they are. But by big, that could refer to both their length, so how many nucleic acids do they have, how many amino acids do they have, as well as their shape. So you can have molecules that are the same length, but have different shapes, and they can then travel differently through the gel. So if you have something that is in a bigger, is kind of like in a big floppy state, it's going to get tangled up more than if you have a nice compact shape that can kind of just whiz its way through. And then if you were to go and you were to stop your gel and go and look and see where the molecules are, even if they had the same like molecular weight, if they had the same length, they would be in different places in the gel, and then you would get really confused. They wouldn't match up with the ladder and things like this. So typically when we run a gel, we're using denaturing conditions where we're going to then have them separate based on their length and be able to compare them better and things like this. But sometimes we'll want to keep things non-denaturing or native so we can do things like see if proteins are interacting with one another. So how do we actually do this denaturing? Well, basically in any case, it's going to start with some heat to help get the things going. And then we're going to use denaturants. So these are going to be things that are going to help unfold the molecules and keep them happy in their unfolded state. In the case of the nucleic acids, we typically have formamide in our loading buffer, as well as urea in the gel itself. And so formamide and urea, what they're able to do is they're able to kind of take the place of the normal hydrogen bonding that's occurring between these molecules. So hydrogen bonding is like this type of attraction that happens. That's the reason why DNA stays double-stranded. Those bases pairing, that's through hydrogen bonding. As well as you can have hydrogen bonding between bases in an RNA strand that's folded up on itself. And the formamide or the urea, they can basically take the places of those hydrogen bonds, satisfy the desires of those bases, but not but but without having them bound to another RNA or DNA molecule. And so we typically have formamide in the loading buffer that's going to kind of get things going. And then in the gel itself, we have urea that can take over. And so we call this like a urea page when we have that urea in the gel itself. But then we also, if we don't have the urea, we can just run like a normal TBE page. And so we'll talk more about TBE in a second, but that's just one of the buffer systems we can use. So that was the case in nucleic acids. In the case of proteins, we're typically using SDS. SDS stands for sodium dodecyl sulfate, and it's a detergent. So it's this artificial soap. It has these like two parts. It's got this long, lipidy, greasy tail and this hydrophilic, negatively charged head. So hydrophilic, water loving, hydrophobic tail, water avoiding. And what proteins, they have hydrophilic and hydrophobic regions too. And their hydrophilic regions are going to be on the outside when the protein's all folded up, and their hydrophobic regions are going to be on the inside away from the water. When you unfold the proteins, well, now you're going to have those hydrophobic parts exposed to the water, which would cause these proteins to kind of like aggregate or clump up, unless you have something that's kind of going to protect those hydrophobic parts. And the SDS is able to do it because it has this hydrophobic tail that can kind of glob onto those parts. And then it also has this negatively charged head, which can hang out with the water. And so therefore, this is going to stay soluble in this unfolded state. And the negative charges are also going to repel one another. So this is going to stay in this nice linear form. It's great for slithering through the gel in a consistent manner. The negative charge is also really important for the protein because proteins can have different charges. So they might be positively charged, they might be negatively charged, or they might be like not really much of either. And it's going to differ from protein to protein. And so therefore, if we're trying to compare the lengths of different proteins, even if they have the same length, if they had different charges, they'd be traveling differently through the gel if they traveled at all and didn't just travel backwards because they were the wrong charge. And so the SDS is going to kind of play double duty with that. Thankfully, proteins often tend to be negative at the pH that we use for native page, but sometimes your proteins aren't. And so one thing that you can do is there's this technique called blue native page, which I have a post on, where basically you use this negatively charged dye that will bind to the proteins. And it's gentle, so it's not going to break up the interactions, but it will give them a negative charge. And so I will post a link to that post I have on that. For proteins, you also might, if you want to unfold things all the way, you're probably going to want to include a reducing agent. So a reducing agent is something like DTT, dithiothiazole, or BME, beta-mercaptoethanol. And what these can do is they can break up disulfide crosslinks. So basically, these disulfide crosslinks are between these cysteine residues, either within the same protein or within different proteins. And they can keep, if you had these happening, you'd have these proteins traveling together, even if you had them both unfolded, if you didn't include a reducing agent. And if the crosslink is just within a protein, you're not going to be able to remove all of its shape. And so you can break up these crosslinks using this reducing agent. These crosslinks are going to not be affected by your denaturing agent because this is only able to break up like attractions, whereas this is an actual bond. But it's a covalent bond, but it's going to be weaker than the rest of the like covalent bonds, the bonds that are kind of like holding this chain together. Those are not going to be affected by the reducing agent, but the ones that are between the different chains or between regions of the same chain, but not holding together the amino acids, those are going to be able to be broken up with the reducing agent, and much more on reducing agents in another post that I'll link to. One of the final decisions you're going to have to make is what kind of a buffer composition do you want to use? In the case of a nucleic acid gel, we're typically using either TAE, so tris acetate EDTA, or TBE, tris borate EDTA. There are also less conventional alternatives, things like sodium borate, lithium borate, or lithium acetate borate, which might be better for various things. But the main two ones that we typically use are either TAE or TBE. And so I have a whole post on this and I'll link to, but basically TAE is better for separating large things with shorter runs, and TBE is better for separating small things with longer runs. We often use TBE for our page gels and TAE for agarose gels, just in my own experience. Speaking of that TBE, I use it at 0.5x. Saves money, reduces heat generation, reduces runtime because you can run things faster, stuff like this. But if you have a really long run, then you're not going to want to do that because you're going to not have enough buffering capacity. And again, much more on this on my TAE versus TBE post. For protein gels, you're also going to have buffer options, and this is also going to influence like the buffer is like in the gel itself too. So you typically have the buffer system is that you use in your outside buffer, the buffer, like the liquid that you have running the gel in, is also going to correspond to the buffer in the gel itself and the gel chemistry. So Thermo Fisher has this guide. I just got this stuff from. Basically, which type of gel you're going to choose is going to depend on things like what size of protein do you want to separate and how much do you care about the integrity of the protein. So basically, for a bis tris gel, this is going to have a more like neutral pH. It's going to be gentler on the protein. So if you want to keep post-translational modifications, things like this, maybe you want to do mass spec and see if there's phosphorylation. Various techniques in which protein integrity is crucial. Then it recommends using these bis tris gels. If you're wanting to get a broad range of separation, you can use this tris glycine gel. So it says like 8 to 250 kilodaltons. If you want bigger, looking for bigger proteins, this tris acetate is often used. And for really small things like small proteins and peptides, people typically use trisine gels. And so those were the main decisions that you have to make when choosing for gel electrophoresis. So you have your gel composition. Do you have agarose? Do you have polyacrylamides? Remember, agarose for those bigger DNA or RNA, polyacrylamide for those smaller nucleic acids, as well as for protein. And then with both of them, you can customize how good they are for bigger or smaller things based on how meshy it is. So a higher percentage gel is better for separating small things, and a lower percentage gel is going to be better for separating bigger things. And then there are also gradient options. And if you need kind of like a range of sizes for the polyacrylamide. One of the main decisions you have to make is going to be denaturing or native or non-denaturing. So do you want to keep those protein complexes together? If so, you're going to want to do a native page. And if not, you're going to use this SVS page. For nucleic acids, you either don't include a denaturing agent, in which case the strands will stay together, the RNA will still have its shape, or you'll add formamide and then have urea in your gel if you want a denaturing conditions. And with the denaturing, in both of those cases, you typically boil your samples with your sample loading buffer containing the denaturant before you load them on your gel. And then finally, you have to choose your buffer. So do you want TAE, TBE? Do you want tris glycine, tris trisine, tris glycine, whatever, all those different options to choose from. And again, I will link to some different resources and things like this that'll help you make those decisions. So hope that helps you understand all the different flavors of gel electrophoresis and how to decide what to use when and things like that.